So I will be talking about some of the efforts we have ongoing to search for QCD axion dark matter with two efforts, the Princeton Axion Search, which is a Princeton PPPL, Caltech JPL involved search for axions, and then also DMRadio, which is a broader collaboration looking at a different mass range as well. So I know not everyone here may be looking for QCD axions, so I'll give the motivation for for looking for them now, which is this very exciting scientific and technological convergence that has occurred. So over about the last decade, there has been new theoretical insights into the QCD axions, in particular, their production mechanisms in the early universe. And this has really motivated this entire pico-eV to EV mass range for the QCD axion. So that's the science side. On the technology side, we've had rapid growth in the technologies of magnets and quantum information science. So this means new materials, this means new sensing techniques, entirely new platforms for doing measurements, which Haystack is now pioneering their use of in axion searches. And these technologies promise unprecedented sensitivity for axion searches. So the community is banding together to, over the next 20 years, to combine these techniques to search for QCD axion dark matter, a comprehensive probe over these 12 orders of magnitude in mass. I'll show a couple of plots that look like this, with mass on the x-axis, the mass of the axion, and the coupling to the standard model, in this case the photon, on the y-axis. I will focus on this micro-eV and below range, and what we're doing at Princeton to search for these QCD axions. So first, I'll start with a bit of motivation as to dark matter, QCD axions, why do we want to look for them? And then I will delve into the Princeton Axion Search, new search searching for axions between 0.8 and 2.1 micro-eV. And then this is really charting a course toward doing both this QCD axion science and charting a course towards the future. And in that context, I'll talk about the DMRadio, which is a broad campaign for sub-0.8 micro-eV axion dark matter. And the ultimate goal, going, as I said, 20 years down the line, is to probe the QCD axion all the way down to nano-eV, where you could probe gut scale physics potentially. So to introduce dark matter, over the past century or so now, an overwhelming amount of evidence, astrophysical, cosmological, has come to light that there must be this dark matter that we don't see. We've got evidence from the CMB, as well as from galaxy rotation curves. Basically, the velocities of stars and gases are much higher than what could be explained with the luminous mass, so there must be some other mass out there. It plays a key role in the formation of large-scale structure, and a dark matter particle would be a particle beyond the standard model. So it has huge implications for cosmology and particle physics. And so for this reason, it's been identified as one of these holy grails in fundamental physics, trying to posit what it is theoretically, and then trying to identify it experimentally. And this has motivated a decades-long hunt for this dark matter. So there have been a number of hypotheses as to what the dark matter can be, but to give you a flavor of these sorts of detection techniques, we'll branch into two groups. The opposite ends of the wave-particle duality in quantum mechanics. So let's start at the higher masses. Let's go above about 8 eV here. Once we're there, we know what the local dark matter density is. It's about 0.3 GeV per cubic centimeter. So if we posit a mass, then we can calculate its number density. And as we get to higher masses, that number density becomes smaller. And you can also you know the virial velocity, it's about 10⁻³ of the speed of light. So you can calculate the de Broglie wavelength. And this tells you that massive particle, these small number density particles, the de Broglie wavelength would be smaller than sort of reasonable size detector that you could create on that. And what these two things together mean for detection is that you're looking for individual scattering events. This is often how we think about particle physics experiments. We have a particle coming in and scattering off of some target, whether it be crystal or some liquid element. So this is these higher masses. So when we go to much lower masses, so well below an EV, now we get very large number densities, and owing to the Pauli exclusion principle, as well as needing to have cold non-relativistic dark matter, we know that this dark matter must be bosons. And now, since we have a very long de Broglie wavelength, for what I'm talking about in some micro-EV, we can be talking hundreds of kilometers potentially. Now we're looking for not individual particles, but interactions with coherent excitation. So over many particles. So now we talk about looking for waves. And waves, like in E&M, they have a frequency that is set by the mass in this case. H nu is equal to m squared. So when I say micro-EV axion, just to give you an idea for this conversion, that's about 240 megahertz. So on each side of this duality, this wave-particle duality, we have sort of a favored candidate. Up near 100 GeV, we have the weakly interacting massive particle, also known as the WIMP. This has been motivated from two directions, both for supersymmetric extensions of the standard model and this what is known as this WIMP miracle. That if you had a thermal relic of roughly the weak interaction cross section near 100 GeV, you would get the abundance of dark matter that you see today. And these two things have motivated a number of searches over the last 35 years to both produce via supersymmetry and detect through direct dark matter searches this WIMP particle. So I show some various detection techniques here using silicon germanium crystals. We also heard a bit from Reina this morning about the cosine experiment, and then also using liquid noble gas TPCs, such as in LZ dark side xenon. So this is the WIMPs in the dark particles side of things. On the dark wave side of things, we have the QCD axion. And this also has had a twofold motivation as dark matter. It was initially proposed in the late 1970s as a solution to the strong CP problem. So when we look at the standard model Lagrangian, it's very natural to add a CP violating term to quantum chromodynamics, this theta GG dual term. But when we go out and we measure, say, the neutron electric dipole moment, it suggests that the theta term is very small, below 10⁻⁻10. So the natural question that comes up is, why does this term seem to be so small? Why isn't it order 1? And so this was solved in papers by Pecci, Quinn, Weinberg, and Wilczek, which said, well, I can take theta to be a dynamical parameter, introduce this new symmetry, the Pecci-Quinn symmetry, and when that symmetry is broken, the theta CP violating term nulls to 0, and by virtue of having this broken symmetry, we produce a Goldstone boson from it, which is the axion. And the axion gains mass through the QCD phase transition. So very soon after this proposal that the QCD axion could solve the strong CP problem, there was an observation by a number of theoretical physicists that it also makes a very natural dark matter candidate, because it has to have feeble couplings to the standard model. So as I mentioned, it can be anywhere between pico-eV in EV scale and mass. So each of those masses in the QCD axion picture corresponds to a different energy scale for the Pechiquin symmetry at which it's broken. So there's sort of a two categories here as well. It can be broken before or after inflation. This is known as the pre-inflationary or the post-inflationary scenario. And the higher the energy scale at which it's broken, the lighter the axion that corresponds to. So for sub-micro-eV axions in particular, they would be present during inflation. And then if we go all the way down to nano-eV, now we're talking about Pechiquin scales that are near the scale of grand unified theory, so 10 to the 16 GeV scale. So what I find really fascinating about QCD axions is that they give a complementary probe into the universe of relative also to like terrestrial searches that we do here on Earth with gliders. You're probing extremely high energy scales by probing the QCD axion. And one of my favorite things about the axion, which really gets me excited as an experimentalist, is the parameter space is almost entirely unexplored. There's been a number of efforts at the cavity haloscope window, so a few gigahertz, ADMX, cap haystack to probe that window, but there's 12 orders of magnitude here that need to be probed. This is the grand challenge that I was talking about, and it's these new techniques that are coming around that promise to be able to help us probe these QCD axions. So how do we probe these axions? Well, as I mentioned, there would be a feeble coupling to the standard model. In this case, I'll talk about the very feeble coupling there is to electromagnetism. So this is known as the inverse Primakov effect. Say that I set up a large DC magnetic field. The axion will convert to a photon in that background field, and so that's sort of like a particles picture. Instead, I can talk about it in a waves picture, where this axion wave at frequency hf plus mc squared converts to an electromagnetic signal at the same frequency. And so now it's a matter of detecting this very feeble electromagnetic signal. So you start thinking about radio techniques to do something like this. So the pioneering proposal was just over 40 years ago by Pierre Sicchivi, where to pick up this very weak electromagnetic signal from the axion, you take a cavity. And if the frequency of the resonant cavity matches that of the axion mass, then you'll get resonant conversion, and you can read out the signal with very sensitive amplifiers. And now we're talking about going beyond things that are more sensitive than the standard quantum limit. Another thing that I find very exciting about this field. So this is what you might do at these higher masses. So like frequencies above 500 megahertz. But now say you want to go to a very low mass axion. Well, now building a wavelength scale cavity is impractical. So what you do instead is you build its analog, which is a lumped resonant LC circuit. The resonance frequency is set by 1 over root LC. And so I show this LC circuit here. In this picture, it's more readily visualize what's going on by modeling the axion as this effective electromagnetic current density. And then we can apply Biot-Savart, and we see that the dominant observable will be this oscillating magnetic field that we pick up with an inductor. And then if the LC circuit frequency matches the mass frequency of the axion, we get a resonantly enhanced current that we can pick up with a squid. Now, we don't a priori know the mass of the axion, so we need to be able to tune these resonators. So in the cavity picture, this is done with a tuning rod. in the LC circuit picture, this can be done by tuning the inductor or the capacitor. So it acts very much like the radio in your car, except it's not a radio for electromagnetic signals, it's a radio for axions. So with that, let me move to the experiments. I'm glad that all of the Princeton team could make it out here to Yale. So I'll talk about the Princeton Axion Search. It's focused at Princeton. We have great collaborators at the Princeton Plasma Physics Laboratory who are real experts on magnets, collaborating with us, as well as some collaborators at Caltech JPL on the amplifiers. So so to motivate this, I showed this plot from the snowmass process earlier this decade, and you'll notice there's, as I mentioned, a lot of experiments going into this into axion searches now. But you'll also notice that there is a hole in coverage in near-term axion experiments between 200 and 500 megahertz. And this represents this transitional range between these two detection ideas that I was showing. This sort of lumped LC picture and this cavity picture. And that's what we aim to address with the Princeton Axion Search, or PXS. So we've been, we're very, very glad about two things. One is about a year ago, we were funded by the Simons Templeton Sloan Moore Initiative, as Alpha here was, to build the PXS. And also with that, PPPL launched a new facility for magnets. Some of you may know that there's a lot of excitement in the fusion community right now to build bigger, stronger magnets. The Plasma Physics Laboratory is a very large part of that. So, we are very, there's a lot of places that we can pull new technology from. Before I go on, yeah, I will be showing a lot of work, but it's not my work. It's the work of all of these students. You've met a couple of them here. There's Nate, Joe, Joel, Roman in the back there, who is no longer a student, but a postdoc with us. He was, I guess, the first one to sign up for this adventure. And then I also want to point out, so Nicholas Rapidis, who is a Haystack alum, now a grad student at Stanford, he was very helpful in some of the early stages of our resonator thinking. And then we had a number of first-year grad students at Princeton who are required to do experimental projects, but they've done amazing work on helping us with various aspects of the experiment. I'll talk a little bit about that, as well as an army of undergraduates. So again, thank you to all of the students. And if you are a student and you are interested in potentially coming to work on PXS, please let me know. So as I alluded to, there's sort of three big elements to an axion search. There's this magnet, there's this resonator, and then there's this readout element. So I'll start with the magnet. So in collaboration with PPPL, we are building a new axion search magnet. And many magnets that we see are made from niobium titanium conductor, and they are immersed in liquid helium. What we are aiming to do with PXS is build a conduction-cooled niobium 310 magnet. So by virtue of being conduction-cooled, cooled with pulse tube coolers, we have no liquid helium. And this niobium 310 conductor, it can operate at higher current densities for a given field than niobium titanium. So this confers mass advantages on the magnet. You can make a lighter magnet, as well as in the future, you can actually go to higher fields. You can, whereas niobium titanium magnets might max out at 9, 10, 11 Tesla. Niobium-310 magnets can go up to 16, 18, maybe even 20 Tesla. So while we won't be starting with at these higher fields, this is something that I'll come back to because niobium-310 will probably play a big role in the axion magnets of the future. What we are aiming to build is a 5 Tesla, 78.7 centimeter diameter magnet with a little bit over a meter in height. So these are, so Yuku Zai is the magnet person at PPPL who's been doing some design work. And as I mentioned, there's been some good student work. This is an initial bucking coil analysis from Zihan Zhu that was a starting point for the sorts of bucking coil configurations that we're thinking about now. So before we build this large bore niobium-310 magnet, there's a number of steps that we need to validate and investigate. So we're building this 5 Tesla a 5 Tesla coil, but it's going to be at 25% length scale. So we're talking about 200 millimeter bore. And this is really to shake out a lot of the things that we need to know before building a large magnet, especially in the electromagnetic, the mechanical, and the thermal interfaces. So as I mentioned, you can operate these magnets at high current densities. We're looking to operate at 550 amps. Niobium-310, it's a brittle conductor. So you need to manage the stress on the conductor to avoid fractures. And then beyond that, we're also validating joint recipes. So when you make these magnets, it's many kilometers of winding, and you can't buy that as one wire, so you have to join spools together. So you want to be able to have a superconducting joint there of niobium-310 wires. And then beyond that, we are also investigating shielding for the pulse tubes. There is a possibility of adverse effects if the pulse tubes are subjected to too high of a field. So to hold this test magnet, we built a test cryostat. You can see Joel and Lyman there mounting it into its frame, as well as the cryostat undergoing MLI blanketing. And these are our high current leads. So in order to operate at 500 magnet at 550 amps, you need to find some way to send 550 amps from 300 Kelvin to 4 Kelvin. And yes, this is a lot of current. And the way that we are doing this is we have copper leads that go from 300 Kelvin to the first stage of the pulse tube at 40 Kelvin. So you'll see them snaking. Try this. Yeah, so you'll see those leads snaking around like this. And then at 40 Kelvin, we switch to high temperature superconductor, specifically visco. And so these get installed in the cryostat, and we have a block of copper shorting the 2 leads. That's not even an inch apart there. And then this is a copper sapphire heat sinking mechanism, because when we have resistive heating, that heat needs to go somewhere to avoid very large thermal gradients. So that is that. And very recently, we had success running 600 amps to 4 Kelvin. The warm end of the high temperature superconducting lead was at 59 Kelvin. They need to stay below 64 Kelvin, or else the HDS leads can go normal. And the 4K plate itself was at 3.4 Kelvin. So this is all, so we can run the current down without the magnet getting too hot. This is sufficient for magnet operation in terms of current lead thermal performance. So now we are very much preparing for this test coil. So here's an opera simulation of this test coil, yeah, as I mentioned, it's about 200 millimeter bore, about the same in the total height. And so a number that I want to point out here is this 223 megapascals of hoop stress. I mentioned that there needs to be some structural reinforcement to prevent fracture, and this is something that the PPPL folks are very much working on. In progress, they are doing trials for wax-based vacuum pressure impregnation. I find this fascinating. Many magnets are impregnated with epoxy for mechanical support, but what they found is epoxy, when you pull it down, you get micro cracks. And the vibrational energy released from those micro cracks can quench a magnet. So you can have many training quenches for an epoxy-based VPI. Whereas with a wax-based VPI, they found that in the magnet community, this can potentially have 0 training quenches and still offer this mechanical support, this hydraulic continuity to other parts of the reinforcement. I also mentioned that we are investigating pulse tube shielding. Here is a Hyperco 50A cylinder that we received about 2 weeks ago now. Hyperco 50A belongs to the Permender class of alloys. It has very high magnetization saturation of about 2.4 Tesla. So it can be a good magnetic shield out to for DC fields out to high fields. It has also been shown to work cryogenically, for example, with ADR magnets. So we will be installing this around the cold stages of the pulse tube.
What kind of wax?
McMaster-Carr wax.
Okay, it's like a paraffin.
Yeah, it's paraffin wax. Yeah.
Sort of a hard paraffin.
No, it's not. I wouldn't even call it hard. It's it just feels like regular wax. Yeah.
No, I think it's surprised for the same reason that's going through your mind. It's like, how's that holding?
So really quickly, I also want to mention this is Joel's CAD here. There's been work towards the full-scale coil and the cryostat that will go along with it. So this is the dilution refrigerator. The magnet sits down here. We're looking right now at an insert-outsert design. So essentially 2 different layers of conductors. There's the cavity that sits immersed. And then this is the beginnings of the bucking coil design. It's a 4 bucking coil array, and then we would have some passage shielding in there. So with that, let me talk a bit about the cavity. I mentioned that PXS is really probing this transitional range between this lumped element picture and this cavity, this traditional cavity haloscope technique. And the resonator very much reflects that. If we have a 787 millimeter bore, we take can have a cylindrical barrel of about 700 millimeters, 77 millimeter diameter for the cavity. And so one can go and calculate what the modes of that bare cavity are. And you find a TM010 mode of about 328 megahertz, TE111 mode of about 290 megahertz. So above 328, things are very much familiar with to the people from Haystack here. This is traditional cavity haloscope techniques. Down here, you're now talking about a different regime, where you're no longer in that traditional picture. So as I mentioned, a number of people in the Princeton group are also members of the DMRadio collaboration, and DMRadio cubic meter has been studying what happens when you want to produce efficiently coupling resonators that efficiently couple to the axion below the TE111 mode of that bare cylindrical cavity. So the approach that we have in mind right now, and this is an incredibly juicy problem, is to sort of combine these traditional tuning rod techniques that you see in haloscopes with the concepts that DMRadio cubic meter has come up with to inform the tuning strategy in that range. So we are working through this. This is a lot of what Nate's been doing. So stay tuned there. We don't have an answer yet. But while we're doing these simulations, we are also building some experimental test beds to shake out what sort of issues we might have. So what we've done is we've created this room temperature test cavity. There's Nate drilling into the top end cap of this aluminum alloy cavity that we got. So the barrel, it's the full scale thing. It's 700 millimeters in diameter, about a little bit more than a meter in height. That's aluminum 1100, and they're aluminum 6061 end caps. And so we can measure the frequency as well as the Q. So the frequency we get is 327.7 megahertz, almost spot on with the analytical calculation. The Q is about 48,000 within 10%, and given standard alloy conductivities, and there's even some uncertainty on that. So we're very much in line with what we expect. So the next step that we undertook was understanding the backgrounds that might cause measurement errors while we try to characterize this cavity. So one thing that Nate here did was he analyzed the resonant frequency as a function of time, and we saw, yes, these kilohertz scale drifts, and we were like, okay, what's going on? And then I noticed at 7 a.m., almost on the dot, things stabilized. And I'm like, that's when campus energy controls turn on. I wonder if there's a temperature variation here. So what we did was we attached a thermometer to the cavity, this linear temperature to voltage transducer. And as you can see, the temperature, which is essentially in blue here, and the resonant frequency, they almost track perfectly over a period of 4 days. So what this informs is the level of background variation that we have in our resonance frequency, this sort of kilohertz scale drifts. And the reason why this now becomes very useful is one is because of this bead pull technique. So to map the mode patterns and understand the resonant modes that we would use to couple to the axion, we can use a bead pull perturbation technique where we take a dielectric or metal bead and put it in the cavity, vary its position, and based on the resonant frequency shift we see, that is actually a proxy for the strength of the field mode there. Of the mode's field there. In this case, given our kilohertz drift, we ended up going with a bead that's actually closer to 2.25 inch ball of substance. One of the things that, so it's been installed inside our cavity. So it's attached to a Kevlar line, and that's wound around a motor there. One of the things that we're going to try to do is map both the electric and the magnetic fields. And one way that this can be done potentially is by comparing the bead pull perturbations that we get from a dielectric and a metallic bead. Because the dielectric beads will give you information about the electric field, whereas the metallic beads are sensitive to both electric and magnetic field. So by differencing those, you can get information about both, about each. We've designed our first tuning rod. It's pretty much ready for fabrication, and this rod will probe those frequencies above 380 megahertz. And while we're doing that, we're also continuing our theoretical investigations. I talked about this very juicy problem that's between 200 and 328 megahertz. So next we have the amplifiers. I talked about these rapidly emerging techniques in quantum information science that can help in axion searches, and the amplifier technology is central to this idea. So when we look at technologies in adjacent frequency ranges, what do we find? Below 200 megahertz, DC splits have been a workhorse for about the last 60 years. However, when you go to above 200 megahertz, for reasons of stray impedance, so intercoil capacitance on the input coils of the squids, for example, you get degradation of the sensitivity. When we look above 500 megahertz, you get things like resonator-based JPAs. These have become a workhorse on Axion searches. Haystack has used them to great effect. But these are inherently one-port devices, and to embed them in the two-port microwave environment, circulators are required. But circulators in the 200 to 500 megahertz range, commercial cryogenic ones, perform substantially worse than their gigahertz counterparts. They have 10 times the insertion loss. There's a similar story there about the follow-on semiconductor amplifiers too. You can get a HEMT now that's 5 or 6 times the quantum limit at 6 gigahertz. But then when you look at 200 megahertz, those HEMTs are 160 times the quantum limit. So this picture here motivates using schemes that are where not only you have near quantum limited amplification like you would get with a JPA or a DC squid, but where you also have up conversion so that you can move away from this frequency range where the follow-on microwave components may not behave so well. So this gets to us to our possible solution. So we have been working with Peter Day and Jonas Zudis on Caltech JPL on a traveling wave parametric amplifier utilizing the kinetic inductance nonlinearity. So this is an effort that's been going on at JPL for about 12 to 15 years now. This is a broadband technique, so that could potentially simplify the tuning over a resonator based amplifier architectures. And the system noise performance that's been measured, so I'll point you to this paper by Malnu and also the NIST team also working on this technology, has shown system noise of a few times the standard quantum limit at 4 to 7 gigahertz. So this seems like a potentially promising avenue to go. The things that we need to do are we need to bring this to lower frequencies. As I mentioned, our band is 200 to 500 megahertz, and we need some form of inherent up conversion. Yeah. So we have demonstrated such an amplifier. So this is the amplifier chip shown here. So to give you an idea of scale, this is about 2.5 millimeters by 25 millimeters. So it's based on a capacitively shunted inverted microstrip of titanium nitride transmission line. And it has an extremely low phase velocity, below 10⁻²c. And what this allows you to do is you can get a lot of wavelengths on a smaller chip, because the gain of the parametric amplifier medium here is essentially proportional to the number of wavelengths of travel. So this is what allows this technology to get down to, in this case, 400 megahertz. Another thing I'd like to point out is previous versions of these traveling wave parametric amplifiers were plagued by very high required pump powers. So you were sending 300 microwatts down to your mixing chamber. But in this new architecture using titanium nitride, that pump powers come down to 300 nanowatts. So it's about a factor of 1,000 improvement there. And lastly, it has this frequency translating component to it, where you can send in a signal at a few hundred megahertz, but the idler tone that's correlated with that signal in a parametric amplifier is at 3 gigahertz. So what you can do is you amplify your signal, you terminate the signal tone, but then read out the idler tone that has all the same information there. This allows you, by essentially doing the follow-on processing at 3 gigahertz, this gets around potential difficulties with the auxiliary with the auxiliary microwave components that I was discussing. So the next steps are so these devices have been shipped from JPL to Princeton. We're working on a setup to measure the device noise. There is also, as I mentioned, we want to get down to 200 megahertz. So there is also now a device architecture that initial measurements have been done on to get gain all the way down to 100 megahertz. So we'll be characterizing these as well. And then one thing that I'm particularly interested in is the possibility of two-mode squeezing to get around the standard quantum limit with these kinetic inductance tubas. So we have a lot of infrastructure under development. Joe showed some pictures of this earlier this morning. We've been installing coax in the DR. This is a variable temperature stage that we installed just last week to thermally characterize. This will be for noise calibration. So you have the stage up here that is isolated from the mounting point by these carbon fiber legs. And then the weak thermal link is actually a 30 gauge copper wire here. So the DR here will be used to study the noise and the device physics. And then we also have a helium-3 cryostat that we've built. As I mentioned, the auxiliary components are something really to pay attention to. You can have a very beautifully performing amplifier, but then have it all ruined by having suboptimal auxiliary components. So auxiliary components and the full readout chain will be a subject for this helium-3 cryostat. One cool thing here that I'd like to point out is, so the first time we pulled this thing down, it took 5 days for the helium-3 stage to get from 300 Kelvin to 300 millikelvin. We were like, that's too long. But we had a side project, both an experimental project that had been starting to characterizing the possibility of using mass-produced flexible graphites as heat switches, and that works swimmingly. So our first try with these graphites, we got our cool down time down from 5 days to 2 days. So we're now we're now prepping to write that up. And yeah, we really like this because a standard solution to this is to go and get a helium-3 gas gap heat switch. This stuff I can, we got to pay for the helium-3. This stuff I bought off of DigiKey for like $60. So yeah, we are very happy about this. So summarize the work on PXS. We are doing a QCD axion search between 0.8 and 2.1 micro-eVs, 200 to 500 megahertz. This involves a very fruitful collaboration with PPPL on this new large bore and niobium-3 tin conduction-cooled magnet. We're aiming to have a copper resonator, so that aluminum is a test, and then we're basically going to take all the lessons we learned from that and make a copper resonator, target Qs of between 100,000 and 200,000, cooled to 40 millikelvin, and a total system readout noise of 7.5 added noise quanta, and we're aiming to be operational in 2027. So, and aiming for DFSE sensitivity, as you can see in this red band here. So with that, let me move on to the other part of the other project that we are involved in at Princeton, which is this dark matter radio. And so this is a collaboration, Stanford, Berkeley, Princeton, MIT are primary experimental institutions. Lindley Winslow here at MIT is our collaboration spokesperson. Kent Irwin is the project director for phases of DMRadio 50 liter and cubic meter. So that brings me, speaking of DMRadio 50 liter and cubic meter, to our near-term plans, which are twofold. DMRadio 50 liter is going to search for axions between 5 kilohertz and 5 megahertz, as you notice, it won't get down to the QCD axion line, but it will still probe a wide swath of axion-like particle parameter space, and very importantly, it will be a test bed for the sensors going beyond the standard quantum limit that are absolutely necessary for doing a gut scale axion search. So if we want, so that doing a gut scale axion search is basically saying we want to take this line here and push it all the way down to the yellow line here. So, and then going concurrently with that is this DMRadio cubic meter project, which would be the first phase of DMRadio to touch the DFSD line, and we hope to do that between 30 and 200 megahertz. So as I mentioned, PXS is looking to do QCD axions between 500 megahertz and 200 megahertz, and DMRadio cubic meter would push that down to 30 megahertz. And so this is being designed under a DOE program, the Dark Matter New Initiatives. Unfortunately, I don't have time to delve deeply into DMRadio, but I really wanted to show some cool photos. So this is the dilution refrigerator, which is testing this cold finger here, and you can see it in the CAD integrated with the magnet and the cryostat. Both of those are under construction right now. We're expecting delivery in the next few months. There's the toroidal magnet for DMRadio, and you'll notice one of your former haystack colleagues, Maria Simonovskaya, holding the cold snout here. Coming back to this toroidal magnet, you'll notice it's not a solenoidal magnet, as many axion haloscopes use. And the idea with the toroidal magnet is that you can separate the large magnetic fields from the resonator components, so you can potentially this facilitates the use of superconducting rather than copper normal metal resonators. And this is a big part of what we've been investigating, the resonator architecture for DMRadio at Princeton. So why do we need a resonator? Well, the scan rate of an axion search goes linearly with the quality factor. And so the higher the quality factor you have, the faster you can get down to the QCD axion line, for instance. So there's been a lot of work on superconducting cavities and resonators at the gigahertz frequencies. So historically, you have these superconducting radio frequency accelerator cavities that through a very long, decades-long optimization, they now achieve Qs of 10 to the 12. And a lot of the lessons have also been translated down to lower occupation number. There are some results actually here from Yale, from the YPY folks, that with 3D cavities for superconducting qubits, they get Qs of 1 billion. So by very careful materials optimization, really paying attention to the fundamental loss mechanisms, they've gotten very, very high Qs. But when we look at this range that we're interested in for DMRadio 50 liter and DMRadio gut, there's very limited exploration of these loss mechanisms, and accordingly, the Qs aren't as high. So sort of state of the art, if you're talking about like around 1 kilohertz, you're talking about a Q of 1 million. If you're talking 100 kilohertz to a megahertz, you're talking about 500K. So several orders of magnitude lower. So this motivates sort of doing what's been done in the gigahertz, but doing it down at a kilohertz to megahertz, really honing in on those loss mechanisms and understanding what they are in this frequency range. So this was Roman's thesis project. Where we built this apparatus to understand these loss mechanisms. As I mentioned, this is not cavities, but it's LC circuits. So you have, here's Roman working on the assembly of the capacitor. So it's aluminum 1100. This is a commercial purity, 99% pure aluminum. That is, it's primarily vacuum gap, but there's some sapphire spacers to hold these plates that are about 20 centimeters in diameter, about 500 microns apart. And then we This is an earlier version of the inductor where we have this form-var-coated niobium titanium wire wound on this aluminum 1100 frame, and that white material going around across the frame is alumina, and all of that gets put in this high purity aluminum shield that's about 40 centimeters tall and 29.2 centimeters in diameter. So the capacitor occupies this top third, the inductor occupies this middle third. So where we were last spring is we got a Q of 710,000 at 301 kilohertz. We had exceeded the state of the art. Roman got to graduate, so he was happy. And then we were like, okay, how can we, so we've got this record Q, how can we do even better? And so what we did was we looked at our loss mechanisms, things that we were somewhat suspicious about. And we were like, okay, the alumina, it doesn't have nearly as good dielectric loss as single crystal sapphire. So we'll replace the rods. One thing that we were really troubled by was our joint quality. There was some suspicion that we were getting some variation between our cool down to cool down because we weren't making consistent joints. So the way that we wound this new inductor meant that we needed one less pair of joints. And so by making those two changes, we got to a Q of 1.74 million at roughly the same frequency. So that's a factor of 3.5 improvement over the state of the art. This is a beautiful plot of Q versus temperature. So that's 1.2 Kelvin, and then we go through the transition of aluminum. And you see that we're actually not quite flattening out at our helium-4 sorption fridge base temperature of 850 millikelvin. So this motivates going colder. So this is our next step. We have a pumped helium-3 fridge that is we know that it works. We're going to hook it up to the resonator. Thus far, we've actually been reading a resonator out at room temperature with coupling coils that come out to room temperature standard voltage preamps. We're going to switch to DC squid readout. We've been these DC squids have been characterized. We've been working on beating down electromagnetic interference in the environment. Lastly, this is a fixed frequency resonator, not a tunable one. So we are going to start investigating these tuning mechanisms and how those might affect the Q. And also, as I mentioned this morning in our meetings, this inductor, that's a square cross section. We're going to change it to a rectangular cross section, an octagonal cross section, make it a bit bigger. And this will be the first inductor that is integrated into the DMRadio 50-liter experiment that's being constructed at Stanford. So don't have time to talk about this, but DMRadio cubic meter, as I mentioned, is the first part of the DMRadio search that will probe DFSD sensitivity. It's based on a 145 centimeter bore conduction-cooled magnet, roughly that height. So it is a very large magnet, as you can see by the scale. It's would be operating at dilution refrigerator temperatures of 20 millikelvin. The introduction paper is here in PRD, and more recently there was a high frequency modeling paper put out. As I mentioned, there is this very meaty problem about how you transition between the lumped element picture and this cavity picture, and that's there's some very nice information and simulations laid out about how you deal with that in the DMRadio cubic meter frequency range. And then accompanying that, very soon we will have a paper out describing the squid readout, going to these higher frequencies up to 200 megahertz, while maintaining 10 to 20 times the quantum noise limit. And as I mentioned, yes, the goal is DFSD sensitivity 30 to 200 megahertz. But let's come back to this goal that I put out there at the very beginning. We want a comprehensive probe of a QCD axion dark matter. all the way down over this pico-eV to EV mass range. We want DMRadio wants to search all the way down to gut scale axions near nano-eV. So that's saying we'll get from QCD axions at 30 sensitivity at 30 megahertz to QCD axion sensitivity at 100 kilohertz essentially. So how might we do that? So that's laid out in this DMRadio gut collaboration paper. So this is really about turning all of those parameters that I've talked about, magnetic field strength, volume, Q, readout, turn it all up to 11. So 16 Tesla, 10 cubic meter magnet. So 16 Tesla, as I mentioned, this is not a field that you can obtain with a nib tie, but the niobium 310 that we're exploring with PXS could potentially reach that field strength. So we're really looking to chart a course for the future here. And as I also mentioned, to reach that DFSZ limit gut scale, we need to evade the standard quantum limit. So this is at a very low frequency where electromagnetic quantum sensing protocols are relatively unexplored relative to the microwave and optical. So a new architecture, the RF quantum up converter, has been devised to do this. And the idea is you couple your low frequency resonator to a gigahertz lithographic resonator by a variable inductor. And so flux from the resonator goes into the lithographic resonator, changes the frequency, and then by interrogating that frequency change, you can do very sensitive flux sensing. So some of you who might have worked on Simon's Observatory might notice the similarity to microwave squid. This is very much a very re-optimized microwave squid, optimized to execute the optomechanical Hamiltonian. Like LIGO-inspired quantum sensing, essentially. And the idea then is to mimic these existing optomechanical protocols that have been executed in the mechanical domain, but bring them to the electromagnetic domain, and especially back action evasion for enhancing sensitivity in DMRadio. So these are pictures courtesy of Katie Van Assendelf, a former Yale undergrad and haystack person. She has been working on these RQUs. So these are various designs of the tunable Josephson inductance. And part of the re-optimization is getting a really high flux to frequency responsivity. So in this case, tuning through one flux quanta gets 600 megahertz of swing on a roughly a 5 gigahertz resonator. So that's actually now been demonstrated. You can see the frequency swing from about a little over 5 gigahertz to about 4.4 gigahertz. So just through one quanta, 600 megahertz flux of response. This up conversion going from the megahertz up to the gigahertz to read it out has also been demonstrated. And since I am running out of time, I want to cover this neat result. So back action evasion is about demonstrating phase sensitive noise, but a step before that is to show that you can have phase sensitive gain so that your device can actually distinguish between the quadratures. So the way that you do this is you amplitude modulate the carrier tone in your microwave resonator. And you amplitude modulate it at the frequency of the input tone on the input coil. And this defines a relative phase between the signal on your input coil and the signal of the amplitude modulation. So you sweep that phase, you look at the output tone power, and as you can see, you're going through these swings of about 30 dB in output tone power. So you really can tell the difference between those two different quadratures here. And it's pretty consistently measured above 30 dB at this point. So in summary, there's this very exciting convergence between quantum measurement, magnet technologies, and this new theoretical insights into axion dark matter detection, promising breakthrough capabilities, not just actually in axion physics, but in a whole lot of fundamental physics. I've covered the work that we're doing on PXS to both do exciting axion science at 0.8 to 2.1 microeV and chart a path toward the future. And then also DMRadio, broad campaign with the ultimate goal of probing down the gut scale PCD axion dark matter in nano EV. Okay, with that, I will take questions. Yes.
Yeah, that was a great talk. Thank you so much. We touched on it a little bit earlier with your slide with the snaking
Yes.
heat sink. Okay, so I'm still like learning a lot about superconductivity and stuff. So is that high volume of current is going to heat up the magnet, which is why you guys have that heat sink there. So is it the resistance in the wire that's causing the heat? And so what's the temperature of the magnet such that like this amount of heat can cause that?
So we have heat sinks on both 40K and 4K.
Mhm.
The heat sink at 40K, so we have these copper leads because we don't have room temperature superconductors.
Yeah.
And so there's many watts of joule heat generated
Mhm.
that we can't like get down to 4 Kelvin, because if it gets down to 4 Kelvin, our cooling power is much less there.
Mhm.
And then the temperature would shoot up, our magnet would go normal, which wouldn't be good.
Gotcha.
And so there's a copper sapphire heat sink there to pull the heat away. I have to double check, but I think it's roughly 40 watts. And then the HTS leads, they actually have some amount of silver in them. So the heat flow through them is about 240 milliwatts. So that also needs to be heat sunk to just remove the heat and not have very high gradients. So I'm not sure if that answered your question.
Well, yeah, and then can you talk about like why the snaking design? That's
Yes.
interesting to me.
Okay, so there are two things pushing here against each other. So if I run current through a copper bar that's moving between two stages, there's two sources of heat flow. There's just heat flows from hot to cold, so there's just the natural thermal flow. And then there's also the joule heat, the I squared R. So as I increase the A over L, that aspect ratio, I reduce the resistivity, the resistance, and I reduce the joule heating, but I increase just the natural thermal flow. And then if I push in the other direction of using smaller A over L, I bottleneck the natural thermal flow, but then I have high resistance, I have high joule heating. So there's an optimum. So it turns out for a given current, there's a particular ideal A over L ratio, and it corresponds to when there is no net heat flux at the top. So basically the thermal flow coming down cancels the joule heat going up. And so the snake, the snake aspect ratio, so that snake is, the cross section is 4 millimeter by 25.4 millimeter, and then it's about 85 centimeters long. That's what determines that A over L doing that optimization. The second thing is differential thermal contraction. We need to make sure that when this copper shrinks relative to other things in the cryostat, that we don't rip apart the cryostat. So there's this copper snake, you can actually bend it by hand. It's like an accordion at that point if you make it like a snake. Yeah.
Gotcha. Okay.
Yeah.
Thank you. That's really, really cool.
Yes.
Does also on the same sort of topic, does this copper wire, it directly connects to a superconductor, right?
Yeah.
So does it connect before or after the 4K stage?
So the connection to the HDS lead is at the 42 stage. Yeah, and then there's a connection between the HDS and superconductor at the 4K stage.
HTS is high temperature superconductor.
Yeah.
Yeah, thanks for the nice talk. Just wondering, so since like PXS is sort of in the middle of in between ADMX and DMRadio, which uses like this two different techniques, I guess what motivates you to choose the traditional resonator versus the lumped element?
Above 380 megahertz, or 328 megahertz. Wait, let me.
Go back, maybe that'll happen.
Here.
Right, so, oh yeah, I guess, this like sits in the like entail of revenue being optimal.
Yeah, where it's easy, where one can readily build a cavity.
Yeah, but I guess like in terms of like. The optimal choice between.
Yeah, so how one optimally goes between the optimization here is to essentially maximize the form factor, maximize the amount of energy that you're coupling from the axion's electromagnetic excitation. And how one goes from sort of this cavity picture to the slumped element picture sort of continuously and optimizes at each frequency is an open question. And that's really what we're trying to answer.